Okay, so here's the latest update from the Wattmeter. So the AD8307 logarithmic amplifiers that I ordered from eBay, say it arrived. Here's the eBay version, and here's the genuine version. Now there is actually a difference between these two. So I did measure them across different ranges of dBm, and fortunately, the relationship between the two is linear. So, for example, at minus 10 dBm, the genuine part registers a value of 404, and the eBay part 400, minus 20 dBm 354, 348. So, fortunately, it's linear. So as I go through there, it varies from -4, a difference of -4 through to a difference of -8. So the eBay part generally is generally working. I mean, obviously it's different to the values I'm getting from the genuine part, but it's certainly good enough for my uses. So I did update the code to display the analog values both from the reflected channel, you can see here, as well as the forward channel. I've actually got it plugged in here at to the signal generator at 10 megahertz at minus 25 dBm. And you can see it's registering a 329. So let me just change that over to the reflected channel, and we can see the results. So as I plug that into the reflected channel, it's 322. So you can see there's definitely a difference there between the two. But fortunately, it's a linear relationship, so I can sort of calibrate that away, I guess. So let's go back to the forward channel again. So what else I've done, so using the readings, the analog pin values from minus 70 dBm to 15 dBm, I've been able to derive a linear relationship between the analog pin value and dBm. And I used, there's a site I used where you can input a series of X and Y values, and it'll derive the relationship, and it just so happens to be, so dBm equals, and then in brackets, analog pin minus 455.39, all divided by 5.09833. And so as you can see, I'm displaying that derived value in dBm right here, so minus 24.79, and the signal generator is actually minus 25. So let me put in a different value, let's say minus 56. Let's go here, minus 56 dBm. And you can see there minus 55.78. Let's try another one, minus, let's say minus 36. Minus 36 dBm, 35.77. So you can see, at least for that frequency, the relationship is working out there. Now, unfortunately, it does deviate somewhat. So let me try that same value at 50 megahertz. So at 50 megahertz, now it's starting to deviate a little bit, 36.16. And then let's go up to 100 megahertz, 36.95. So it's kind of holding good from between, let's say 1 megahertz and 30 megahertz, but you go a bit outside that, and the values start to deviate. But anyway, this is all part of the fun. So I'm back at 15 megahertz now, and as you can see, minus 35.97. The signal generator is minus 36. So that's the forward and reflected channels installed. What I'm definitely going to do next is start working on the encoder, and I mentioned that before. I'm going to have a little menu in there, a little calibration menu in there, so I can adjust a few of the internal values. Now I do need to install additional switch, unfortunately. I thought I could get away with just using the encoder, but I realized in order for me to have a sort of a back button functionality on the menu, I do need an additional switch. The single switch on the encoder really isn't enough. So anyway, that's next. Here's the encoder here. Again, this is cheap Amazon stuff, and I've used these encoders elsewhere. And I'll show the code that I'm using for the encoder. Again, I got that off, I think it was Instructables, but I'll find the link and include it in the following video. it does use the two interrupt pins that are available on the ATmega 328. So anyway, that's in the next video.